You know that feeling, right? When you're just drowning in information articles, research papers, maybe internal company reports, and you're just wishing someone could, I don't know, cut through all that noise and just give you the absolute essence. Well, today we're diving deep into a technology that promises to do just that, not only for us humans, but for artificial intelligence itself. We're talking about enabling AI to really understand complexity and, maybe more importantly, to actually take action in the world. Welcome to the Deep Dive. This is your shortcut to being genuinely well-informed. We try and pack it with surprising insights, maybe just enough humor to keep you hooked. So today we are embarking on a really fascinating journey into LangChain and the incredibly dynamic world of generative AI, specifically agentic AI. We've synthesized a whole collection of expert insights, deep dives into the core concepts, the practical implementations, really aiming to give you that kind of deep, practical understanding you'd expect, say, working at a top tech company, like a FA-Angie level understanding.
This deep dive is really designed to equip you with the knowledge you need for setting up genuinely intelligent, robust, and production-ready systems, moving beyond just playing around to real-world impact.
Yeah, and what's truly transformative here, I think, is how LangChain really positions itself as this orchestration framework. It takes what could easily be a super daunting, fragmented process, building these AI apps, and turns it into something modular, understandable, and actually highly efficient. We'll meticulously explore its core components, understand exactly how they fit together, and ultimately, how this empowers AI systems to reason, to plan, and to act with this kind of unprecedented autonomy. It's really about demystifying the intricate yet actually quite elegant interplay between these large language models and the complex demands of real-world interaction.
Okay, so our mission today is to unpack all those intricate details of LangChain, everything from its foundational concepts right up to the sophisticated architecture that drives these advanced AI agents. We want to make sure you grasp every crucial detail you need for building these cutting-edge, intelligent applications. We're going to understand not just what these components are, but really why they exist and how they unlock these completely new possibilities for AI. So yeah, let's really unpack this piece by logical piece.
The why of LangChain taming the AI beast.
So to really get LangChain's approach, we first need to understand the problems it was actually built to solve, right? Let's start with the why. Why is building these LLM-powered applications from scratch? Why is it so surprisingly complex? You might think initially, oh, it's just an API call, right? Send a prompt, get a response. But the reality is far, far more intricate. It involves what feels like this endless array of moving parts. We're not just talking about the large language models, the LLMs themselves, but also, specialized embedding models that give the AI a sense of meaning, vector databases to store those embeddings efficiently, document loaders to pull in all your company data, text splitters to chop it up. It goes on and on. Each of these components is its own piece of tech, often with its own API, its own unique requirements. Getting them all to work together seamlessly. It feels like trying to build one of those complex Rube Goldberg machines, where every single piece needs to be custom engineered just to connect perfectly.
Okay. Exactly. And just imagine the sheer difficulty of trying to code that manually in that kind of environment. If you've painstakingly built an app from scratch, maybe tightly integrated with, let's say, OpenAI's API, and then for whatever reason, maybe cost, maybe strategy, you decide you need to switch to Google's Gemini, or maybe a different embedding model for some specialized capability. What happens then?
Yeah, nightmare scenario.
You literally have to rewrite, often from the ground up, huge critical parts of your application's code. This isn't just a minor tweak. It's a major, time-consuming, and frankly, error-prone refactoring job. And given that this tech is still so new, it's evolving at this incredible pace, manually managing these integrations, it just becomes incredibly complex and fragile. It puts this huge burden on developers, right? It pulls their time and energy away from focusing on the unique intelligence, the secret sauce of their app, and forces them instead to grapple with the underlying kind of repetitive plumbing.
And that is precisely where LangChain steps in, acting as this crucial abstraction layer. It's an orchestration framework, fundamentally designed to handle exactly this heavy lifting and all that fiddly interfacing. So instead of developers getting bogged down in the details of connecting different APIs, managing complex data flows, ensuring compatibility, LangChain effectively says, look, you focus on your core idea, on the unique logic of what you want your AI to do. And I'll take care of the complex plumbing, the foundational architecture. It provides these pre-built functionalities, standardized interfaces. It enables this plug-and-play interaction between components, and that drastically reduces what everyone knows as boilerplate code, all that repetitive, boring, but totally necessary code you write just to make different systems talk.
Yeah, and what really transforms the development process with LangChain is how it simplifies the whole life cycle of building these robust AI applications. It's about moving away from those custom, fragile integrations towards something more standardized, resilient, and crucially for production, scalable. So let's dive into some of the most compelling benefits of actually using LangChain in, real production setups.
Okay, so among these benefits, one really stands out, and it's right there in the name. The concept of chains, the pipeline concept. The name LangChain comes directly from this foundational idea. Chains let you effortlessly link different components, different tasks, into a logical pipeline structure. Could be sequential, could even be parallel. Think of it less like rigid code, more like an intelligent assembly line for your data and your AI models. The real elegance here is that one component's output just automatically becomes the input for the next component. No manual coding needed for those transitions, no managing intermediate data formats.
Right.
This simple idea fundamentally shifts how we build AI. It turns what was bespoke, fragile code into these modular, reusable pipelines. That's a huge leap in engineering efficiency and reliability. Plus, LangChain lets you build incredibly sophisticated workflows because it natively supports complex chain structures. Sequential, sure, but also parallel, where tasks run concurrently to save time, or even conditional chains where the path changes based on results. That's what makes these really sophisticated adaptive workflows not just possible, but actually straightforward to implement without tons of custom code.
And what becomes immediately clear when you start working with chains is just the clarity and modularity they bring. Building on that, a massive advantage, one you really can't overstate for any serious production environment, is model-agnostic development. This means you can basically switch your underlying large language models, say from OpenAI's GPT models to Google's Gemini or whatever else comes along with literally like 1 or 2 lines of code changes in your configuration.
Well, really, just 1 or 2 lines.
Yeah, pretty much. Your core business logic, the unique intelligence of your app, stays completely isolated from the specific model implementation underneath. This is incredibly powerful for production. It gives you flexibility, potential cost optimization by choosing the best model for the job, and resilience against API changes or even outages from a single provider. It basically future-proofs your application against the rapidly changing LLM landscape. You can always leverage the best model for your needs.
That is huge. And it's not just about the LLMs either, is it? LangChain offers a truly complete ecosystem. They seem to have thought meticulously about pretty much every need a developer might have when building an AI app. You get this huge variety of pre-built tools, components for almost everything. You need to ingest data, robust document loaders for cloud storage like Google Drive, S3, local Excel, PDFs, Markdown, web pages, you name it. Need to break down huge text into manageable pieces. Over 50 types of specialized text splitters. Need to turn text into numerical representations for semantic search. Lots of high-quality embedding models available right out of the box. And crucially, it supports seamless integration with a vast array of different vector databases and even traditional databases. This comprehensive ecosystem means your company will rarely, if ever, have trouble finding a pre-built interface for whatever component you need. Less vendor lock-in risk, too, which is always good.
Definitely. And finally, something absolutely essential for any truly effective conversational AI, the ability to remember context, to respond intelligently within an ongoing interaction. That's memory and state handling. LangChain provides incredibly robust and flexible solutions for this. It meticulously helps maintain context across multiple turns of a conversation. This isn't just nice to have, it's critical for natural, flowing, genuinely intelligent interactions. Consider this common scenario. A user asks your system about, say, the assumptions of linear regression. Your system gives a great answer. Then, without explicitly mentioning linear regression again, the user follows up with, okay, also, could you give me a few interview questions about it?
Ah, right, the it.
Exactly. Without sophisticated memory, a basic AI might miss the implied subject of it and give generic interview questions, or maybe nothing relevant at all. LangChain, however, lets the system remember that prior context, linking the follow-up question directly back to linear regression, so it generates highly relevant interview questions specifically about linear regression. The whole interaction feels seamless, intelligent, coherent. It fundamentally elevates the user experience. This capability is foundational for building truly useful chatbots, AI assistants, any multi-turn dialogue system.
The building blocks LangChain's core components in detail.
Okay, so now that we've really nailed down the why behind LangChain and its big benefits, let's break down the how. To truly harness this framework, to build those intelligent production-grade apps, mastering its 6 core components is absolutely key. So let's dive right in, starting with the very first, arguably most fundamental piece of prompts.
Right. At its heart, the role of prompts is basically to serve as the precise instructions you give the LLM. You're guiding it to perform specific tasks, generate particular kinds of output. They're like the initial spark that directs the AI's vast knowledge. And one particularly powerful technique here is few-shot prompting. This involves giving the LLM just a few carefully chosen examples of input and the desired output. By seeing these patterns, the LLM effectively learns to generalize that behavior to new, unseen inputs without needing explicit rules for every single case.
Okay, so you're kind of teaching it by example.
Exactly. For instance, imagine you're building a customer support system to triage tickets. Instead of writing complex rules, you could use few-shot prompting. You'd show it examples like input, my monthly statement seems incorrect, output.billing issue. Input, my internet connection keeps dropping, output technical problem. Input, I have a general question about your services. Output.general inquiry. End quote. Just providing those few specific examples lets the LLM intuitively grasp the underlying intent. It learns how to accurately categorize new tickets, even with slightly different phrasing. It significantly cuts down development effort for classification tasks.
That's a great illustration. Prompts are the LLM's guiding hand. But what happens after the LLM generates a response? Often they just return raw, unstructured text, right? Like a paragraph or a sentence.
And that presents a significant practical problem for integration. Unstructured text, while humans can read it, is notoriously difficult to integrate programmatically with other systems like databases or APIs. You can't just feed a free-form paragraph to a database and expect it to magically pull out the customer name or order ID.
Yeah, makes sense. It's a data bottleneck.
Precisely. The critical solution here is output parsers. These ingenious components are designed specifically to convert those raw, unstructured LLM responses into predictable, structured formats. Think JSON objects, CSV files, or even highly validated Pydantic models. This transformation is crucial because it ensures consistency, robust validation, and ease of use when connecting LLM outputs to the rest of your application's infrastructure. And what's really powerful for building flexible systems is that LangChain's output parsers are designed as reusable classes. They can work with any LLM, whether that specific model natively supports structured output or not. That model agnosticism is a huge benefit.
Okay, so what kinds of output parsers are there?
Well, within LangChain, you'll find several types. The string output parser sounds simple, but it's incredibly useful. It just takes the LLM response and ensures it's consistently converted into a plain string. You might wonder why you need a parser for something so basic, but its key role is standardizing the output format, especially for ensuring seamless chaining in a complex pipeline where every component expects a consistent input type. It's a reliable bridge.
Got it. Then I guess there's one for JSON.
Absolutely. The incredibly versatile JSON output parser. As the name suggests, it converts the LLM's output into JSON format. This is paramount because JSON is the universal standard for data exchange across pretty much every programming language and system today. Turning the LLM's text into JSON makes its output immediately consumable by other systems, databases, other APIs, front-end apps. It basically makes the LLM speak the language of modern software.
Okay, that makes sense for interoperability. What about more complex validation?
For the most advanced production-grade scenarios, you have the Pydantic output parser. This is really powerful. It's built on Python's renowned Pydantic library, which is famous for its robust data validation and parsing. Its key features provide a really strong foundation for reliable AI apps. It enables rigorous data validation, meaning you can define precise rules. For example, ensuring a customer rating is always an integer between 1 and 5.
Ah, so you can enforce constraints.
Exactly. Or that a price field is always a positive float. It also lets you set default values if fields are missing. And crucially, it performs implicit data conversion, or type coercion. So if the LLM returns the string 32, but your schema expects an integer, Pydantic automatically converts it to the integer 32, preventing common type errors. Plus, you can apply even more granular constraints using Pydantic's field function. This isn't just syntax, it's about guaranteeing data integrity from your LLM. You can define strict rules, like a CGPA must be between 0 and 10, add descriptions, or even specify regex patterns for validating formats like phone numbers or emails.
So comparing that to just using, say, a typed dictionary in Python or a JSON schema, when would you really reach for Pydantic?
Good question. Pydantic often hits the sweet spot for robust Python projects needing strong runtime data validation and that automatic type conversion. Type dictionaries give you type hints for static analysis, which is great, but no runtime validation. So a malformed LLM output could still crash your code at runtime. JSON schema is language agnostic, excellent for interoperability, but you need external libraries in Python to parse and validate against it. Pydantic often feels the most seamless and Pythonic for building reliable Python applications that consume LLM outputs.
That's helpful. And you mentioned something about LangChain doing things secretly behind the scenes with these parsers.
Ah, yes. It's quite clever, especially with advanced parsers like the Pydantic one. When you use LangChain functions like with structured output, the framework isn't just passively waiting. It secretly generates a specialized system prompt that gets sent to the LLM along with your main query. This carefully crafted prompt acts as an implicit instruction, telling the LLM something like, "You are an AI assistant extracting structured insights. Your response must be in valid JSON format adhering to this specific schema." This covert guidance is what nudges the LM to produce structured output, even if it doesn't natively support it. You can also tweak this using the method parameter in with structured output. JSON mode is for standard JSON, while function calling is crucial for agents where the LLM needs to output a specific tool call object, not just data.
Okay, this idea of seamless connections and guiding the AI, that seems like a good transition to Runnable's standardizing interaction. Let's rewind a bit, maybe to late 2022, when LLMs really started taking off, moving from research labs into practical applications. The creators of LangChain saw pretty quickly that if developers were going to build real production-grade apps, some kind of unifying framework was desperately needed. The early landscape was fragmented, right? Lots of separate components, the LLM, prompts, parsers, retrievers. But crucially, they didn't follow the same set of standards, made them really hard to connect seamlessly.
Yeah, the problem with those early disparate chains was significant. Manually connecting them meant writing specific chain functions for every single combination. You'd have an LLM chain for basic stuff, a retrieval queue chain for RAG, and so on. This led to a really steep learning curve. Developers had to learn all these different chain types, and it resulted in heavy code full of custom glue logic just to bridge the gaps between components that weren't designed to talk to each other. It was inefficient and brittle.
So LangChain's answer was the Runnables API. How does that fix things?
It fundamentally standardizes how all components within LangChain interact. Now, every single component, from a simple parser to a complex custom function, is conceptually a runnable. What this means practically is that every runnable object has a standardized invoke method. This simple yet profound standardization changes everything.
How so?
It's like giving every single building block the same universal connector. It allows components to be plugged together like Lego blocks. Developers can create highly flexible, complex, robust workflows with incredible ease. Whether it's a prompt, an LLM call, a parser, a retriever, even your own custom Python function if it's a runnable, it speaks the same language and connects seamlessly. It makes composing sophisticated pipelines intuitive.
And to make that composition even clearer, there's the LangChain expression language, LCEL, right, using the pipe operator.
Exactly. LCEL leverages the intuitive pipe operator to chain runnables together in a very clear, declarative, sequential flow. It looks almost like writing a mathematical equation for your AI pipeline. Data just flows gracefully from one operation to the next. It really enhances readability and maintainability, especially for complex applications.
Okay, so what are the key building blocks, the primitives within LCEL?
Good question. Let's look at the crucial runnable primitives. The runnable sequences for those linear pipelines where components execute one after another. A classic example is prompt model parser. You'd use this to, say, generate a summarized text. Input goes to prompt, guides the model, output gets parsed. Clean, linear, easy to follow.
Makes sense. What about doing things in parallel?
For that, you have runnable parallel. This is incredibly powerful. It lets you execute multiple distinct branches concurrently. Imagine you want your AI to generate a summary and extract key entities from a document at the same time. You set up parallel paths for each task. Runnable parallel runs them simultaneously, which can significantly speed things up, and then neatly returns a dictionary containing all the results. Super efficient when parts of the output don't depend on each other.
Okay, cool. What else?
There's runnable pass-through. This one's clever and often essential. It basically passes its input directly to the next step without changing it. Why is that useful? Well, it's great for injecting additional context alongside the main input. For example, in an RA setup, you might want to pass the user's original query along with the retrieved documents to the final LLM call. Runnable pass-through makes sure both pieces of info are available downstream.
Ah, I see. Useful for keeping track of things. And the last one.
Runnable Lambda. This is where you can integrate your own specific custom Python logic directly into a LangChain pipeline, making it a first-class citizen. It lets you wrap any Python function you write and turn it into a runnable. This means your specialized data cleaning, proprietary pre-processing, custom business validation, whatever unique code you have can be seamlessly plugged into the workflow. It offers unparalleled flexibility for tailoring the pipeline to your exact needs.
Beyond basic LLM retrieval augmented generation, RAG.
Okay, so with all these tools for building pipelines, you might be thinking, LLMs are amazing. They write code, poetry, answer questions. What else could they possibly need? But while they're incredibly powerful, standalone LLMs, especially in a production context, have some pretty significant inherent limitations.
Indeed. There are three major persistent problems you often run into. Problem 1. Private data access. LLMs are pre-trained on vast public data sets. They simply cannot answer questions about your company's specific, internal, proprietary information. Ask it, what's the XYZ company's updated leave policy for 2024? A standalone LLM has no idea. That data wasn't in its training. It's private to your organization.
Right, it just doesn't know it.
Exactly. Problem 2, knowledge cutoff date. LLMs are trained on historical data. Their knowledge is static up to a certain point in time, their cutoff date. They can't give you accurate info on very recent events. Ask what were today's Premier League results, or what are the latest breakthroughs in quantum computing this week. Well, I likely say it doesn't know, or worse, give a confident wrong answer based on old data.
Okay, so they're stuck in the past, essentially.
Pretty much. And then there's the really tricky one. Problem 3, hallucinations. This is a critical issue where LLMs can confidently generate incorrect, nonsensical, or completely fabricated information. This happens if they lack relevant context or if the precise answer isn't in their training data. They don't know what they don't know, so they might just invent plausible-sounding but factually wrong details. Very convincingly sometimes.
Which is obviously a huge problem for trust and reliability in production.
Absolutely.
So this raises a really important question for anyone building real-world AI apps. Is there a robust, scalable way to fix all these fundamental limitations?
Retrieval Augmented Generation, or RAG, is the definitive answer here. RAG fundamentally changes the game. It works by connecting an LLM to an external, up-to-date, and potentially private knowledge source. This allows the LLM to provide current, accurate, and specific information it wasn't originally trained on. Instead of relying only on the LLM's internal knowledge, RAG dynamically retrieves relevant information from your own data right when the user asks a question and provides it to the LLM in explicit context. Think of it like giving the LLM an instant on-demand reference library tailored to your specific questions.
And crucially, you mentioned RAG is often cheaper and simpler than fine-tuning for these specific problems.
Yes, significantly so. Fine-tuning means retraining a massive model on new data that's computationally incredibly expensive, needs specialized expertise, and you have to redo it every time new information comes out. With RAG, the paradigm shifts. You just update your external knowledge base, which is far faster and cheaper. The LLM can immediately access the new info without retraining. It's not just cost. It democratizes using LLMs with proprietary data, avoiding that massive retraining effort. Plus, it powerfully grounds the LLM responses in verifiable facts from your data source. This drastically reduces hallucinations because the LLM has specific context to work from, more trustworthy output.
Okay, this sounds like a critical technique. Let's break down the RAG architecture. You mentioned an indexing phase first.
That's right. This is the preparatory step where you build and prepare your external knowledge base, getting it ready for fast retrieval later on.
So step 1, document ingestion. This uses LangChain's document loaders, right?
Exactly. Their job is to load your raw data from all sorts of sources, PDFs, web pages, text files, cloud storage like Google Drive or S3, and convert them into memory as standardized document objects.
Right.
These document objects are a specific LangChain format. Each one holds the page content, the actual text, and importantly, metadata, like source file, page number, author, custom tags. This metadata is super useful later for filtering.
How does the loading actually happen? Eager versus lazy?
Good point. You have choices. Eager loading pulls in all documents at once. Fine for small data sets, but can be slow and memory heavy for, say, hundreds of PDFs. Could bottleneck or crash. Lazy loading is more scalable. It returns a Python generator, loading documents one by one only when needed. Much more memory efficient for large files and big data sets. Keeps your app stable under load. And a big plus for LangChain, if there isn't a built-in loader for your specific data source, you can build your own by inheriting from base loader. Many existing loaders were community contributions showing its extensibility.
Okay, data ingested. What's next? Step 2. Text chunking using text splitters. Why do we need to chunk?
Chunking is crucial. You break down those potentially huge documents into smaller, manageable chunks. Two main reasons. First, LLMs have context length limits. They can only process so much text at once. Feed it a whole book, and it might only really see the beginning and end. Smaller chunks ensure everything gets processed. Second, smaller, semantically coherent chunks significantly improve the quality of semantic search later. The embeddings we generate will be more focused, representing clearer ideas.
And you control this with chunk size and chunk overlap.
Correct. Chunk size sets the max length, again, 1,000 characters. Chunk overlap sets how many characters overlap between consecutive chunks. That overlap is vital. It helps retain context that might get lost if a sentence or key idea is split right down the middle, ensures smoother transitions. A good rule of thumb is maybe 10–20% of the chunk size for overlap.
What are the different ways to split the text? I imagine just cutting by character isn't ideal.
Right. The simplest is the character splitter. But yeah, it can lead to awkward cuts mid-word or mid-sentence. The recursive character text splitter is the most common and generally recommended. It splits hierarchically, trying to keep semantic units together. It uses a list of separators, starting with the biggest, like double new lines for paragraphs, then single new lines, spaces, and finally characters if needed. It tries the biggest separators first. Much better at keeping meaning intact.
Can you make it aware of the document type, like code or markdown?
Yes, that's context-aware splitting. The recursive character text splitter can be adapted. You can give it custom separators relevant to the structure, like class definitions in Python or heading levels in Markdown. This stops it breaking a chunk of code right in the middle of a function, for instance. Preserves logical units. And then there's the more experimental idea of semantic meaning-based text splitters. The goal here is to split based on shifts in meaning, not just length or structure. You might split by sentence, embed each one, then cluster semantically similar sentences into chunks. This holds a lot of promise for even more precise retrieval, though it's more complex.
Okay, chunks created. Now step 3, embedding generation. This turns text into numbers.
Exactly. This is pivotal. Text chunks are transformed into dense numerical vectors or embeddings using an embedding model. These embeddings capture the semantic meaning. Think of them as numerical fingerprints. Chunks with similar meanings, even if worded differently, will have similar fingerprints in this high-dimensional space. This enables semantic search, understanding the meaning of a query, not just keywords.
And where do these numerical fingerprints live? Step 4, vector stores.
Precisely. Vector stores are specialized systems designed to store and efficiently retrieve these numerical vectors. Key features make RAG work at scale. Storage. They store the vectors and their associated metadata, original, doc, page number, author, tags. Great for filtering. Similarity search. Critically, they excel at finding vectors, and thus document chunks, most similar to a query vector. That's how RAG finds relevant info. Indexing for fast search. To do this quickly, they use advanced indexing like clustering or approximate nearest neighbor, ANN lookup. ANN lets them search millions or billions of vectors super fast by narrowing the search space, not checking every single one. Makes your app fast and scalable, CRU operations. And like databases, they support create, retrieve, update, delete for vectors.
You often hear vector store and vector database. Is there a difference?
Yeah, it's a subtle but important distinction. A vector store focuses primarily on vector storage and retrieval, the core engine. A vector database is basically a vector store with added database-like features, crucial for enterprise production. Things like distributed architecture for scalability, backup restore, ACD transactions for data integrity, concurrency control for multiple users, authentication for security. These extras make it production ready.
Can you give an example of a vector store or database?
Sure. A popular one, especially for getting started or for smaller projects, is ChromaDB. It's a lightweight, open-source vector database. Good for local dev, prototyping, even small to medium production. Its structure is intuitive. Tenant database collection, like a table, document, embedding plus metadata. You add documents, they get unique IDs, and that metadata is key. You can use it for really powerful filtering during search. Like find documents about Q3 earnings only from 2023 and only authored by finance. Super precise retrieval.
Okay, indexing done, knowledge base ready. Now the retrieval phase of RE, this is where retrievers come in.
That's right. The retriever is the active component. It fetches relevant documents or chunks from the data source, usually the vector store, in response to the user's query. We can categorize retrievers based on their data source or their search strategy.
Okay, data source first.
An example is the Wikipedia retriever. It queries the public Wikipedia API. Important difference. It mainly uses traditional keyword matching, not the semantic search based on embeddings we discussed for vector stores. Shows the variety of access methods.
Got it. What about search strategies?
The most common is similarity search. Straightforward. Retrieves documents whose embeddings are numerically most similar to the query embedding, finds things conceptually closest. Very effective for direct relevance.
But sometimes you need more nuance.
Exactly. For that, there's maximum marginal relevance, MMR. This is more advanced. It balances relevance to the query with diversity among the results. MMR makes sure the retrieved documents are pertinent but also distinct from each other. It avoids getting back 5 chunks saying almost the same thing, which isn't very helpful for the LM, gives a broader, richer context.
What if the user's query is vague, like how to be healthy?
That's where the multi-query retriever shines. It tackles ambiguous queries. It cleverly uses an LLM to generate multiple, more diverse but related subqueries from the original vague one, like what are healthy foods, how much exercise is needed, what are good sleep habits. It searches for each subquery, gathers results, merges them, removes duplicates, gets comprehensive info even from vague starts.
Clever. And one more, contextual compression.
Yes, the contextual compression retriever. This is advanced, aimed at improving retrieval quality by compressing or shortening retrieved documents before sending them to the LLM. Imagine a retrieved document talks about both photosynthesis and the Grand Canyon, but the query was only about photosynthesis. This retriever uses an LLM to extract only the relevant sentences about photosynthesis, discarding the Grand Canyon stuff. This gives the main LLM concise, focused context, reducing noise, improving accuracy, and helping manage the context window size.
Wow, okay, so many different retrievers. Why the variety?
It's fundamentally driven by the challenges in building sophisticated Arctic systems. They're not just options, they're specialized tools for specific problems. Key for building advanced RAG applications that go beyond basic performance. If your simple ARG isn't working well or struggles with certain queries, chances are a more advanced retriever is part of the solution. Future high-quality, reliable production RB systems will absolutely leverage these kinds of specialized techniques.
The intelligent agent's autonomy in AI applications.
Okay, here's where it gets really interesting, maybe even a bit sci-fi. What if an AI could go beyond just understanding and responding? What if it could actually think, plan, and execute tasks in the real world autonomously? This brings us to AI agents.
Right. At its core, an AI agent is an LLM-powered system that can autonomously think, decide, and take actions using external tools or APIs to achieve a goal. The key difference, especially compared to the chains we talked about, is the level of autonomy. Chains follow predefined, static steps like a flowchart. Agents dynamically figure out their own steps based on the problem, the current context, the available tools. They're much more adaptable, handle uncertainty better, vastly more autonomous. An agent essentially has 2 core capabilities. First, reasoning and decision-making. This comes from the LLM itself. It breaks down problems, often using techniques like chain of thought prompting, where it outlines its reasoning steps, leads to more accurate results.
Okay, so the LLM is the brain.
Exactly. Second, action taking. This is enabled by external tools. Tools are literally the hands and legs of the LLM. They let it interact with the real world, get information, perform operations beyond its internal knowledge. The true marriage of a powerful LLM with a diverse set of practical tools is what creates an intelligent, action-oriented agent.
So what exactly are these tools in LangChain?
Simply put, a tool is just a Python function, packaged in a way the LLM can understand and call when needed. LangChain offers a rich ecosystem. There are built-in tools, pre-built by the LangChain team for common use cases. Think DuckDuckGo, search for web searches, Wikipedia query run for lookups, even a Python REPL tool for safely executing Python code, ready to use out of the box.
And you can make your own.
Absolutely. That's the power of custom tools. This is where your specific company logic comes in. Need the agent to talk to an internal database. Call a legacy API. Fetch data from a proprietary system. Perform a unique calculation. You wrap that functionality in a custom tool. This lets your agent extend its reach far beyond general knowledge into your specific operational domain.
Okay, so how does the agent actually use these tools? That's tool calling.
Yes, enabling LLM action via tool calling. The crucial first step is tool binding. This is the process of registering the available tools with the LLM. This teaches the LLM 3 things. What tools are available, what each tool does via a description, what input format each tool expects, its schema or arguments. You typically do this using the bind tools function on the LLM object, giving it a list of the tools you want it to be able to use.
And how does the flow work when a query comes in?
It's fascinating. The LLM gets the query. Based on its reasoning, chain of thought maybe, it decides if a tool is needed. If yes, it doesn't run the tool itself, it generates a specific tool call object. This specifies which tool to use and the exact arguments needed. This tool call is then passed to the agent executor.
Agent executor, what does that do?
The agent executor's role is critical. It's the doer. It takes the tool call from the LLM and executes the tool on the ground, makes the API call, runs the Python function, whatever. The output from the executed tool is then returned to the LLM as a tool message. This new information, this observation from the real world, lets the LLM continue its reasoning. Maybe it needs another tool. Maybe it has the final answer. This iterative loop thought, action, observation is what gives agents their dynamic power.
Can you give a concrete example?
Sure, think about a currency conversion agent. You can create 2 custom tools. Conversion rate to fetch the current exchange rate, say USD to INR, and convert to do the math using an amount and a rate. You bind both tools to the LM. A user asks, convert 100 USD to INR and tell me the rate. The LLM reasons it needs the rate first, generates a tool call for conversion rate, executor runs it, gets the rate, for example, 83.5, sends that back to the LLM as a tool message. Now the LLM knows the rate. It decides its next step. Call the convert tool, the amount 100 and the rate, 83.5. Executor runs that. This multi-step interaction, driven by the LLM's reasoning and the executor's actions, solves a complex real-time problem.
That makes it much clearer. Are there standard ways to design these agents, like patterns?
Yes, there are several agent design patterns. One very popular and transparent one is the React agent. React stands for reasoning plus action. The core of React is a continuous, iterative thought-action observation loop.
Okay, walk me through that loop.
Sure. Thought. The agent, the LLM, thinks about the problem and what it needs to do next. This internal monologue is often visible if you enable verbose logging, which is great for transparency and debugging. Action. Based on the thought, it decides which tool to use and what input to give it. Translates reasoning into a concrete step, observation. This is the result returned by the tool after the executor runs it. Real-world feedback.
And this loop just keeps going.
Exactly. The agent processes the observation, generates a new thought based on it, maybe takes another action, gets another observation. It continues until the agent determines it has found the final answer or achieved its goal.
So just to be crystal clear, the agent is the brain doing the planning and deciding which tool, and the agent executor is the hands actually running the tool.
Perfect analogy. Agent is the strategist deciding what needs doing. Agent executor is the operational arm making the calls, running the functions, doing the actual work.
Why are React agents so useful?
They're great for multi-step problems, anything needing more than one step, and tasks requiring tool usage like web searches, database lookups, API calls. Crucially, they offer transparent and auditable reasoning. You can see the agent's thought process step by step, builds trust, helps debugging, and to make creating them easier, LangChain offers LangChain Hub. Think of it like a GitHub for prompts. It has predefined optimized prompts for React and other agent types. The React prompt, for example, explicitly guides the LLM to follow that thought-action observation structure. When the agent is done, it outputs a special agent finish object with the final answer, ending the loop.
Wow. Okay, today we have taken a truly phenomenal deep dive into LangChain. We've traced its evolution, really, from simplifying basic LLM interactions right through to enabling these genuinely autonomous AI agents. We've explored how it systematically tackles those fundamental problems: context limits, lack of real-world interaction, using powerful ideas like runnables for modularity, RH for grounding in data, and agents for orchestrating complex tasks. I feel like you now have a really comprehensive practical understanding of how to build these robust, production-ready AI applications that go way beyond simple chatbots.
Yeah, and connecting you to the bigger picture, LangChain really does significantly lower the barrier to entry for building complex generative AI applications. For any organization, really. It's not just about the cool tech features. It's about providing robust, flexible, scalable solutions that are pretty much indispensable for production environments. It fundamentally lets you focus your energy on the intelligence, the unique value of your application, instead of getting bogged down in the plumbing and infrastructure. This framework truly empowers developers to move beyond basic AI and build deeply intelligent, adaptive, action-oriented systems that can tackle real-world challenges.
So what does all this mean for you listening right now? Think about these agentic capabilities, AI systems that can reason, dynamically plan, autonomously take action using tools. How might that transform not just how you build technology, but maybe how you interact with technology every day in your life, in your work? What complex multi-step problems, maybe ones you thought were just too tricky for automation, could you imagine an AI agent solving now that you have a better sense of how they actually work under the hood? The possibilities feel truly boundless, and honestly, like we're just scratching the surface. Keep exploring, keep asking questions, and definitely keep joining us for more deep dives into the accelerating future of technology.